and welcome to this week's Happy Maths Hour. This is Pythagoras Theorem Story 2. Last week we dealt with the history, and today, Tony, what are we
there's
doing?
a bit more history, but we're going to look at one of the proofs of Pythagoras' theorem, which is a jigsaw proof. And I hope you'll all like it. It's not going to be difficult at all. We're just going to do a lot of chatting about things, aren't we, Caroline, as we usually do?
Yeah, Happy Maths Hour is very relaxed.
Yes. Okay, so what you see in the middle of the screen there is a couple of the solutions to this jigsaw, and Caroline's recently done this with a class of year 9, haven't you, Caroline?
Yeah,
15.
And it was 14, 15-year-olds, and is it about 14-ish, and they enjoyed it. Actually, it's 13, 14-year-olds, and it's people that, well, this wasn't a class that tends to be interested, but some aren't, and they were all interested in doing this activity, every single one of them.
Can you hear a noise, Caroline, in the background?
I can hear a printer printing. It's okay. It's not
no, I haven't got a printer on here.
Oh, really?
Yes.
It sounded like a printer.
Oh dear. Well, we can't do much about that, actually. I don't know where the sound's coming from.
We've got a ghost.
Right. Well, now, this is quite a busy slide. And as Caroline said, we did talk about the history of Pythagoras' theorem last week, but we didn't look at this picture. But what you see is that this spans 5,000 years, from the Egyptians right through to current time. And we haven't got any actual recorded writing from the Egyptians about Pythagoras' theorem. We have from the Babylonians, but not from the Egyptians. But, well, we believe, don't we, Caroline, that it's more than likely that the Egyptians were well aware of it, because in designing and building the pyramids, which were very precise, they had to have a knowledge of geometry, of triangles, even trigonometry.
And right angles. There's a lot of right angles in the pyramids.
Yes. To get the
accurately.
Yes, to get the top of the pyramid, accurately over the middle of the base, it doesn't happen by accident.
No, which is why, even though there's nothing, we have physical evidence, if not actual proof, that they used it. It looks as though they used it, even if they didn't have a name for it. They certainly wouldn't have called it Pythagoras, of course. What I love about this line, though, is that you're looking at 3,000 before the current era, BCE. So before, basically, we're into 2000 BC. So that is going all the way back. It's more than 5,000 years ago that the pyramids were built, and using it's Pythagoras' theorem isn't something that man invented. Pythagoras is something that man discovered and uses to make our environment straight.
Yes, indeed. Well, yes, it is quite confusing. I mean, I grew up with BC and AD, and it's now BCE and CE, isn't it?
CE, I don't even know what it is now. Yes, I see it there, but I haven't got it straight in my head yet. So before the current era and the current era.
Yes, indeed. So a lot of knowledge was carried both ways, actually, along the trading routes, what we call the Silk Route across from China and India and through to the what we call the Middle East now, and the Mediterranean, and of course the sea routes as well, where there was a lot of trade over the centuries. I must say, I think the truth is that in those eras, BCE, most of the knowledge went from east to west rather than from west to east. Although there was a passage of knowledge both
That's a
ways, I have to
reasonable
say.
assumption. Yeah.
Well,
we're certainly trading in both directions. But
absolutely. And we did receive, what I'm trying to say is we did receive a lot of information from India and China at that time. And what we see is that although the Babylonians had knowledge of Pythagoras' theorem, as you see from the clay tablets there and the inscriptions, and we talked about those last week, so did the Chinese, but we didn't talk about the Indian mathematics, and we will do that a little later today. And we didn't mention Pythagoras. We did mention Fermat's last theorem, which is similar to Pythagoras, as you see up on the top right there, which is that for a to the n plus b to the n equals c to the n, there's only one possible value of n, and that's n equals 2, which gives you Pythagoras' theorem. And it's impossible to find a, b, and c which obey that formula, follow that formula for any other value of n. And that was only proved not very long ago, in fact, within the last 10 years by Andrew Wiles. But what we didn't talk about was
Fermat's last theorem.
Yes, indeed. Last, because...
Was that what they called Fermat's last theorem? So it
yes,
has
indeed.
now been proven, yeah, because throughout my childhood, it was like Fermat's last theorem, nobody's been able to prove it. And it's such a simple concept, as you said the other day. It's a super simple concept. You can see the formula for a to the n plus b to n is not equal to c to the n for n not equal to 2. Super simple to look at, but it took how many years? 300.
Over 3. Well, yes.
No, because he was born in 53, but he proved it. Yeah, well over 300, nearly 400 years for somebody to actually prove it. And you had a story about that, Tony.
Ah, yes, indeed. Well, all right, I'll tell the story now.
Oh, we can tell it later. We can put everybody in suspense and tell the story later.
No, you've introduced it, Caroline. Andrew was born in Cambridge, actually, so he's well known here. And the story is, he went to the local library as a boy of about 12. He was very interested in maths at the time, and he was reading maths books that he found in the library, and he read about Fermat's last theorem. Well, he'd learnt about Pythagoras' theorem, and he thought this must be easy. And so he played around with it then, when he was in his teens, and tried to prove it, because although he knew it hadn't been proved over these hundreds of years, he thought it couldn't be that difficult when it was so simple, as Caroline just said, to actually state it. And it was his life's ambition to prove the theorem, okay? And he realized...
Some people spent their whole lives attempting it and failing. So there was a possibility that he would not have succeeded. Just to fill that in, lots and lots and lots of people had attempted to prove it, hadn't they, over the decades?
Well, yes, I mean, along with his studies and then his job and other research, he tried, and he didn't. And he was, by this time, he was coming to 20 years ago, he was a professor at Princeton University, and so he still hadn't proved it. And so he shut him, this story is, and I think it's true, he shut himself in his room, and it said for 7 years. And of course he went out to do the normal things, and and had meals with his family and that sort of thing. But he told everybody at Princeton that he was working on this, and he actually, the story is, he didn't do any other research or teaching. He just completely focused on this proof. And then there was a meeting in Cambridge, and I think it was about 2013, but I might be out by a year. And nobody knew he was going to do it. He then gave a lecture in which he announced his proof, which he'd done, okay? And my husband and I went to a party that evening, and he was there, and everybody was so excited. It was like the most amazing party you can imagine, given by the head of department, John Coates, who's himself a number theorist. And, people were just, oh, wow. However, subsequently, some glitches were found in the proof. So it was another couple of years before it was finally published. And everybody around the world was then aware that it actually had been proved. But it is very difficult. And it took a couple of years even to sort it out, even though Andrew had proved it. As I say, there were a couple of details that were almost, but they were important, that needed to be solved. So that's the story. And now I'm really quite horrified, because I thought, well, horrified, a bit strong, but I mean, I had always thought of Andrew as quite a young man, but I now realize he's 70 this year. So he's not quite so young.
Than me. not anymore. Yeah, they catch up with you eventually, don't they, Tony?
Yeah, yes, indeed.
I'll catch up with you soon.
Anyway, let's go on. I just haven't mentioned yet why we've got this map in the lower map of the two, which shows you North Africa and Spain and Portugal there in sort of yellow, and then there's various shades of sort of red colors. And that is the Islamic culture as it spread through North Africa and up into Europe. And that brought into Europe a great amount of learning from the Islamic culture. And then that eventually came through to the rest of Europe. So the rest of Europe were well behind at the time. And when the what we called the Moors, in fact, the people from the Central and Middle East, and these people who come across, these Muslims who come across and taken over Spain, what's now Spain and Portugal, when they were driven out of Spain and Portugal, in fact, they were invited to the Vatican. Some of the scholars were invited to the Vatican to give lectures on the mathematics that they knew, and astronomy and science that they knew, that wasn't known in the rest of Europe, because we were the Pope actually, and the leaders of the Europe were worried that we would lose quite a lot of that precious knowledge, which we hadn't actually, we just needed to know. So they brought it into Europe. They brought a lot of knowledge of mathematics into Europe. And that's not so generally known, but it is really important. So what we're still talking about is this theorem that's named after Pythagoras, but was known thousands of years before Pythagoras and used. And it states that when you have a right-angled triangle, the area, which is c squared, if the hypotenuse of the triangle is c, is equal to the sum of the areas a squared plus b squared of the squares on the other two sides. So that's Pythagoras' theorem. Now, this rule was known to ancient civilizations, including the Indians and the Chinese and the Greeks, and was recorded in Mesopotamia as far back as 1800 BCE. But actually, who discovered it? Well, it can't reliably be accredited to one person or even to one culture. We're not really sure who was first.
Yeah, it doesn't. What's interesting is that one imagines that, well, one imagines it might not be true. It could have been one person first, but it'll be that the standing on the shoulders of giants that came before you. It'll be somebody in one culture and then sharing something, and then it growing and people having realizations and taking it in a different direction or further in a different culture. So it's probably a group effort, I would have said, a team effort, would be my guess.
Well, yeah, I'm sure you're right. And in fact, interestingly, it's the converse of Pythagoras' theorem that was widely used, which was that if you've got the square on the hypotenuse equal to the sum of the squares on the other two sides, then it's a right angle. So to get an accurate right angle, people made instruments that were actually obeying that rule. So all used rope, but more likely they had what we call a set square. So the fact that they were actually...
about it, a set square is typically, well, they would have to be, but are they set to work linearly on that? As in,
it must have, if it has a right angle, then it must obey Pythagoras' theorem.
If it has a right angle, I'm wondering if it actually is that they do the measure. No, like so that it's integer length.
I
don't know. It probably isn't. I'm probably just.
Well, it might not be integer lengths, Caroline, in every set square, but that is what was there is evidence that the early civilizations used what we call the Pythagorean triples, which is integer lengths. Yes.
Right. Yeah.
So this is a picture here of a sort of quite an imaginative one with this colourful sky behind him and his robes. He's in orange like you, Caroline.
Yes, I like the orange, but I'm a bit horrified by his use of Pythagoras. Well, yes. So I don't know if I want to be associated with this one.
Oh, well, I'm surprised. Why? I mean, he
what used it for?
Well, I see. Well, yes, he lived around 800 BCE, but even there, it's not very clear exactly which year he was born in and when he died. But he wrote a lot of mathematics, and his Bodhayana Silba Sutras were sort of the geometry of Vedic mathematics, and he recorded a lot of really important information and ideas there. And there's a quote, a translation of one of the things he wrote was that the rope stretched along the length of the diagonal of a rectangle. Imagine it from the picture there, right? Makes an area, and it must mean it's the area of that square on that length, BD.
That's what we think, yeah.
Which the vertical and horizontal sides make together, and it must mean that that is the vertical side AD and the area of that square, and the square on the horizontal side AB. So that is how it was conceived and written by Bodhayana, and he was a mathematician, a priest, and an architect.
Sorry, I love the fact that he starts with a rectangle, and that's an interesting insight that the diagonal of a rectangle is a nice starting point for a square base. Square.
Yes, and That's right. Now, these, as I said, these Sulba Sutras were appendices to the Vedas, and Vedic mathematics is still really important in India, isn't it? And it is similar to the mathematics of the rest of the world, but as it was developed, the emphasis is slightly different, and the way it's expressed is slightly different in Vedic mathematics. Or Indians might tell you it's very different. Yes, it wasn't just Hindu. Well, originally, I think it was written in Sanskrit, but it's not just the Hindus. Also, the Buddhists shared in this Vedic mathematics and all the scholarship around that.
But they're certainly very keen to spread the knowledge, the system, the methods used in Vedic mathematics. So it's definitely worth investigating if you're interested, because apparently it does simplify or make. I'm not quite sure what like, for example, multiplication. Long multiplication, it helps people.
I think there are lots of ways of doing multiplication and other forms of calculation, and I think there are ways in Vedic mathematics that that are quite neat and a little bit different. Anyway,
this is a bit that creeped me out about this mathematician, priest, and architect. The worrying part is the priest.
Oh, well, I see.
Go on, Tony.
Well,
constructing altars and with ritual sacrifices. That meant they were killing things on these altars. They were using the Pythagoras, the Pythagoras principle, to actually make very precise altars so that they could kill things. So that's the thing that creeps me out.
Oh, I see.
They had to be very precise, and there's no room for error, so they had to be absolutely precise. So they use mathematics for it, but it's those things that religion do, where they have to kill things to appease the gods and things, and I don't like that. Makes me unhappy.
Okay. Well, be it as it may, I suppose sometimes they put the products of their industry there, their farming or whatever. But no, I think you're right. Actually, but actually, Caroline, if you're going to slaughter a beast to eat it, is it worse to slaughter it to sacrifice it on an altar?
Okay, I suppose if you're going to eat it and it's a creature that you eat, then I suppose fine.
I think if we eat meat, then we really shouldn't be critical of perhaps of other people who, for the reasons you've just stated. Anyway, let's look at this. Let's look at this diagram. Okay, so now you see a diagram which is described, I believe, in the Sulba Sutras as a way of finding the area of a triangle, of a square that's equal to the sum of the areas of two smaller squares. So it's Pythagoras' theorem, isn't it? So what you do is you have the two smaller squares, A, B, C, D, and P, Q, R, S, and along the edge of one of these sides, along the edge PQ, you mark PX, which is the same length as AB. So that length is one of the edges of the smaller square, as it were. Okay. And the other edge, PS, is the length of the edge of the larger square. And so you have SX as, you have that triangle PSX, and there's a square on the hypotenuse, and that is, as was stated by Bodhayan, which is again equivalent of Pythagoras' theorem, in its area, the area of SZYX or SXYZ is the sum of the areas of the other two squares.
Mm-hmm.
So in a way, that's a different sort of, slightly different way of referring to Pythagoras' theorem. Now, some of the information here comes from the maths history from St Andrews, but if you look Badhayana and the Subha Sutras up on the internet, you'll find a lot more information, and you'll find information about Vedic mathematics if you're interested. So I just want us to think a bit about these Pythagorean triples that we met last week. There are infinitely many of them. What are they? The integers a, b, and c such that a squared plus b squared equals c squared. And we
sorry, point out that there are infinitely many triples out of integers. So sometimes you find there's a limited in some combination because we're specifying integers, but this is integers. So in other words, if they're not whole numbers, there's still an infinite amount of them, but this is with integers, an infinite amount of them. I love it. Right.
These are Pythagorean triples, and it's a somewhat surprising result. And the way you find it, as we discussed last time, is that you just take any two integers you like, m and n, and then the hypotenuse, c squared, will be m squared plus n squared. The shorter sides will be m squared minus n squared and 2mn. So here's an example. If m and n are 2, m squared plus n squared is 4 plus 1, which is 5. That's c squared. And m squared minus n squared is 3. And 2mn is 4. So that gives you a 3, 4, 5 triangle with integer edge lengths. And if you take m is 3 and n is 2, you get 3 squared plus 2 squared is 9 plus 4 is 13. 3 squared minus 2 squared is 9 minus 4, which is 5. And 2mn gives you your 12. And there it is. And these are roughly to scale.
So wait,
the third one.
For any two positive integers, any. So it could be 1 and 100,000 billion.
Yeah, any two. You can use this formula, these formulae, and you can generate a Pythagorean triple.
Wow.
Well, it is nice, isn't it?
That was a big surprise to me. That was a huge surprise to me. If you'd asked me how many do you think there are, I would have assumed, number one, that it was a limited amount, and and I love the fact that you can actually calculate it. You got any two positive integers, and you can work out what the third. Well, no, not what the third. You can work out a, b, and c. Love it.
Yep. Yeah, that's it. Now then, this is you can, so we've just said, so that means you can draw infinitely many right-angled triangles with integer edge lengths. Now, there's a theorem, not his last theorem, but what's called Fermat's right triangle theorem. And here he's saying it's not possible for all the four lengths now, A, B, C, D, to be integers if you join two right-angled triangles, as you see in the diagram. Now, what you have
the hypotenuse against one of the non-hypotenuse of
one of the legs.
You're doing that.
He calls it a leg.
A leg, okay, one of the legs at the end. And so his theory is it's not possible for them all to be integers. You can't have A, B, C, and D being integers. We know that B, D, and A can be integers. We know that D, B, and C could be integers, but then the A wouldn't be an integer or the C wouldn't be an integer, depending.
It wouldn't fit. It wouldn't fit. Yeah, and because you've got an infinite supply of right-angled triangles, which we just agreed, you might think that it would be possible from that infinite supply to find two that you could match up like this. And it's not a different. but it's not possible, and it's not a difficult proof that it's impossible. And so it's a sort of surprising result, however. Okay. Now,
Again, this Fermat dude did some had a lot of insight there.
yes. And now this is Andrew Wiles, about Andrew Wiles and Fermat's last theorem, and there it's another incidence of that it's not, something is not possible. Okay. And again, it's something that you would think might be likely to be possible, but because obviously you can try any value of n and there are infinitely many of them, but it's not. You can't find anything except n equals 2 for which that formula is right. It works. So there you are.
It's quite simple with Fermat, wasn't it? If you made the statement that he's making, he didn't, well, everyone has the onus of proof. You won't accept something in mathematics without it, but he's making the negative statements, which kind of is also simpler to state.
Yeah. And anyway, so these are two theorems.
You knew that without proving it. To me, the first one, the right-angled theorem, is just, and he was right. I love it. Okay, keep going. Sorry.
Well, these two are theorems, both by, originated from Fermat, and in both cases he said something wasn't possible, but he did prove one and not the other. Yeah. Okay.
And he did prove the one about the right-angled triangle. Cool. Right.
So now we're going to talk about a jigsaw. It's a lovely jigsaw. It's one of my favorites. Simple, okay. There's only 7 pieces, and there are only 4 different shapes. Okay, well, the squares and triangles, but the 4 triangles are all the same, and the squares are different sizes. Okay, but there's something special about the squares. So the green square is exactly the same edge length as the shortest edge of the triangle.
Right. Okay. Yeah. There's 4 blue triangles, and the green square matches they're congruent triangles, and the green square matches the shortest length of course, all 4 triangles because they're congruent. Okay. We've got that clear.
Carolina, I wondered if you were going to demonstrate this. Have you got your visualizer up and running or not? Never mind. Never mind. We can just talk about it.
Sorry.
Next time we'll do another puzzle, a different one, and you can demonstrate it on the visualizer. Okay.
Absolutely, with pleasure. I've got
with
my
pieces
sorted out.
I knew you got these pieces. Yes.
I've got 20 sets of them.
I guess because you did them with your class, didn't you? Did this particular jigsaw with your class. And by the way, as is noted there, it was originally, this is adapted a little bit, but not much. It's really as it was given in this Chinese manuscript about 200 years BCE.
That's
okay,
amazing.
So the orange square, okay, the edge length of the orange square is exactly matching to the middle length of the longer leg, if you like, of the right-angled triangle.
We call that B square. We can call the green one would be an A square, and the gold one would be the B square. Okay.
Yeah, you don't need to algebraicize it, Caroline, but you can.
We've been talking about it.
Yes.
So, okay. But if you do facilitate this with young learners, that what Tony says is do not mention Pythagoras at all until you get to the final conclusion, which we will lead you to.
Yeah. Even if they've and that's true whether or not they've met Pythagoras before, because if they have met it before, it then is revision, and if they haven't, they will actually discover something they didn't know about, but they will discover it. So if the pink square, well, obviously that one as the other two match the lengths, that one must match the length. So the jigsaw puzzle is about putting these pieces together, okay? And it's called the make squares puzzle. And the two challenges here, one of them is to find 5 pieces, not all of them, with 5 pieces making a square, okay? Fitting the edges together, matching the edges. And the other challenge is to fit 6 of these pieces together to make a square. So it's move the pieces round, you can match the edges, make a square. Imagine it. Okay. And there are 3 solutions. The 5-piece solution takes the biggest of the squares, the pink one, and puts those copies, those 4 identical triangles around the edge, and it makes a square. And that square will fit into the frame that's drawn below. It'll fit exactly into the frame. Now we have 2 different 6-piece solutions here. Spot the difference.
Well, just differences of the other 2. Oh, the difference between the pink one and the green and gold one.
No, difference between solutions 2 and 3.
Difference between solutions 2 and 3. It uses the same pieces. They're just in different configuration.
Well, the orange and green squares are clearly in different places.
Yeah.
Right? Yeah. And you make rectangles now with the blue, each with a pair of blue triangles.
Right, yeah. But they're both, in that respect, they're both the same. Solutions 2 and 3 have 2 rectangles made from the blue triangles. But I suppose that's the only way I can see where you can actually make a square using those 2 smaller squares.
Yes. And again, all 3 solutions, of course, one at a time, will fit into the frame. So, what can you deduce?
They're all the same size, so they are congruent. The shape that they make, the square that they make.
Well, the area, now let's think about areas. The area inside the frame is going to be the same. And so what can you deduce from the 3 solutions? Well, put the solution 1, the 5-piece solution, into the frame and remove 4 blue triangles. What have you got left?
1 pink square.
And that is the area that's covered up. Okay. Now, instead of doing that, put solution 2 in, okay, into the frame, and then remove the 4 blue triangles. And what have you got left?
2 squares, but you're removing the exact same area both times, even though they make one. You're removing 4 triangles from both, and they are congruent triangles. So you're removing the same area both times, so the area left of the green and the orange must be the same as the area of the pink
square. Yeah. And whether you do that with solution 2 or solution 3, it's
the area is the same. The area
so you it's, if you do this with a class of teenagers, even 12-year-olds, even 11-year-olds, and you ask them what they notice, and you sort of ask key questions, what do you notice about the areas? What's still covered up in that frame? Some of the learners in the class will say, oh, the area of the pink square must be the same as the area of the green and orange put together. And you will always get some children who will spot it, and then the others will say, oh, yes. And then, if they have never met Pythagoras' theorem before, then you should really warmly congratulate them. Say, they're great, how wonderful, you've discovered this theorem. And it's a really really important theorem. Okay, and if they have met it before, you can they may recognize without prompting that it is Pythagoras' theorem, but you know they'll soon realize that it is Pythagoras if they met Pythagoras before. Now, of course, it's not really a proof, because this fit might not be 100% accurate. There might be a tiny little difference, you know, but I wouldn't sow any seeds of doubt like that. And when they're older, they can actually turn this into a formal proof. So this is actually what people call a proof without words. You know, it's if you think about it, it seems pretty obvious, but if you have to write it down, then it needs, because of the conventions, the agreements between mathematicians, you need to state it quite carefully, and that can be done. That can be done. Okay, so let's move on. Now, before they ever meet Pythagoras' theorem, students should do the puzzle and find these solutions for themselves and talk about them. Now, that's that's what I think should happen if possible. And so, with guided discussion in which the teacher asks the key questions, the students will notice that if the 4 triangles are removed from each arrangement, then the areas in the frame still covered must be equal. We discussed that. And okay, so there they are. And then, in fact, if you look around the classroom, what different learners have done, what I just briefly gave you a glimpse of will be that there might be other solutions that apparently look different, that different children in the class have got. Not just the ones you see here, but slightly different solutions. And that's great, because that's something that needs to be discussed as well. Because some learners might have got one that is called solution 1, but what about the solution underneath it? Is it the same solution? Well, spot the difference between solution 1 and the one underneath it.
Solution 1, the one underneath it, it's flipped.
Yes, you could either
symmetry. No matter which way you turn it round, it's still different. It's still the same but different to solution 1. It's not the same as solution 1. It's the same as itself, but different to solution 1. So it's flipped. It's flipped over. It's like the mirror image of it.
Yes. So exactly, and both of them have rotational symmetry of order 4. You can turn them round and fit them 4 ways, and but as Caroline's just said, one's a mirror image of the other. Now, that is something that the learners in the class might observe, but actually, for the purposes of what we're doing, we're going to say that the one below is a repeat, or it's equivalent to the solution 1 above. Now look at solution 4. Is that different from solution 2 and solution 3, for example?
Oh, sorry, solution 4, solution 3. Okay, sorry, I was assuming solution 4 was the second pink one. I see it now, it's down below. Okay, solution 4, that is similar, using the English term similar, to solution 2, but the diagonals are different on 1. Let me see. It's flipped over. The diagonals are, number 1, the diagonals are different. Number 2, it is, some of it's reflected, some of it's a mirror image, and some of it's just different.
Well,
the configuration is similar, but the way that the triangles are placed is different.
That's right. When Caroline's talking about the diagonals of the rectangles, what she means is that the two blue squares have been placed differently together to form the same rectangle, but the blue squares are differently placed.
The
And
blue
so,
triangle.
yes.
Sorry,
So
instead of square. Sorry.
so solution 4 is a variation or a repeat or an equivalent of solution 2.
Okay. So
Looks like.
equivalent. We can call it an equivalent. Okay. Yeah.
What about solution 9?
Solution 6 is solution 9. Solution 9 looks similar to solution 3 because it's got an L shape. The triangles form an L shape, as do they with solution 6. So if you couldn't see the diagonals of the triangles, we can see that all three are actually different. Their configuration is different.
Yes, I mean, if you were just looking at the rectangles and you couldn't see where the triangles were there, then solutions 3, 6, and 9 would all seem the same, but you can spot now that they're actually variations, but they sort of, in some ways, belong together. So as a group activity, students will, as we said, they'll find some of these variations around the class. We're calling them equivalents, and they could name them after the students who found them. You know, one of them could be Caroline's. So what's called solution 1 could be Caroline's solution, all right? And the one underneath it could be Tony's solution. And then we'd say, well, really, they're two versions of the same solution. And solution 2, solution 4, you might name them after Peter and Mary in the class. Well, it's just one possibility. You might do. But the point is that the children can then take ownership of them and say, oh, I found that one. Yours looks a bit different, but it's actually equivalent to mine.
It's one of those lovely poster activities, isn't it? Get all the possibilities up on a poster, and you can name them according to the first person that discovered it.
Yes.
As you say, and that's on the poster.
Yeah, you could make a poster with the variations. Yeah. Okay, yeah. So we'll look at that in a minute. So this is an opportunity for students to revise what they know about reflections and rotations. So not only can they revise about Pythagoras' theorem if they've met it before, but whether or not they've met Pythagoras' theorem, this is an opportunity to think about reflections and rotations. And it comes naturally. You don't have to find all of the possibilities. You can just look at the ones the children around the classroom have found. And they could look at different variations if you have the time and see how many they can find. So what about these? How many fractions are there? Are there?
2, 4, 6, 8 fractions. No, I don't know. What, 2?
Are they all different?
4, 6, I see 8 fractions. Are they different? 3, 6, let's see. 50 over 100 is a half, so that's equivalent to that one. Oh, you mean they are equivalent, some of them. Let me see. 75 over 100 is 3/4. 15 over 20 is 3/4. 7 over 14 is a half. 21 over 28, now that's a bit different. 3 over 6 is a half. 21 over 28. So that would be
3/4 again.
3/4. Oh, that's 3/4 again. Okay, so there's only 2 fractions there.
Absolutely.
And
right. So what we're saying about the fractions there is similar to what we're saying about the solutions of this puzzle. But in fact, fractions have infinitely many equivalent forms, don't they? I mean, we can write a half in infinitely many different ways. as long as the number on the bottom or the denominator is double the number in the numerator. But these solutions to the puzzle, actually, there are a finite number. You could find them all. You could put them all on a poster. So let's have a look at them. So we've already discussed that these, as Caroline said earlier, they're either they're two versions of the same thing or equivalent, and with one's a reflection of the other. Now, here are all the other ways that you can put the triangles into those other two shapes with the 6-piece solution. There are exactly 8 different ways you can do it. Now, they all do look the same, but spot the difference. Solutions 2, 3, and 4 and 5 are distinct solutions, although they all look alike at a first glance. But the difference is the way the blue triangles are fitted into those rectangles. And similarly with 6, 7, 8, and 9. So
right, so the triangles have got the same 4 variations, but because the squares are in different position, it's 4 different.
So if you look at solutions 2 and 3, they're symmetric. There's a sort of, and the others are not symmetric when you consider where the triangles are placed, and so they only have 4 variations, whereas solutions 4, 5, solutions 4, 5, 6, 7, and 8, they have 8 variations each, and that all makes 56 variations in all. So actually, some people, really perceptive people, might have already noticed that we've changed the numbering a little bit from the very first time we looked at these solutions, and this is to assist this classification. I've numbered these solutions 1 to 9 like this. So there's solution 2, and notice it's symmetric, and there are that solution rotated by 90 degrees, by 180 degrees, and by 270 or 90 degrees anti-clockwise. That's 4 variations of solution 2, and you see 4 similar variations of solution 3.
So these are equivalent to equivalent fractions,
in the sense that they belong together.
I'm not sure they belong together.
They're equivalent to each other, right? You haven't got 4 distinct solutions there with solution 2, and another 4 with solution 3. You've got variations on the same one. And here with solution 4, notice here there are 8 variations of that, because there are also reflections of all of the different. When you reflect solutions 2 and 3, because they're symmetrical, you get a copy of the same thing. But when you reflect solution 4, you get something that looks different, and there you have 8 different versions of that. So the first 4 are solution 4 that's got the number in it, rotated. So you see the smaller square, the green one, appears first in the bottom right corner, then in the bottom left corner, then in the top left corner, then the top right corner as you rotate it.
Right, yeah.
And the ones on the right are reflections of, so this one here, if you can see my cursor, is a reflection of the one that's got the number 4 in it. And then these are all rotations of this one, or you can name where the axis for the rotation, but they're all reflections of this one that's numbered 4.
Okay.
Now, I'm not saying that in a class you'd want to make a poster with all of these on. You might feel you hadn't the time. You might think it was a little bit obsessional to want to find them all. But some children would actually really like doing that, and it's certainly a possibility, and it's certainly oh, I found my eyes sort of almost going squint-eyed trying to doing all these pictures, but it's
Yeah.
but here they are. Now we've only got up to number 4. That one, by the way, is one of the ones that appeared in the beginning. And now we've got solutions 5 and 6 and all the variations of those. Again, 8 variations of each one. And solutions 7, 8, and 9, again, 8 variations of each one.
Yep.
And I promise you, they are all different. In some sense, they are all different in some sense.
I believe you.
Yeah. So I've written here at the top, it is an activity to revise Pythagoras' theorem and transformations at the same time. So it's a rich activity. It's got plenty of potential. And it's really important when you're teaching. Some of you may not be teachers, but you may have children and you may think about, their experience in school. It's really important that they can get their hands on things and actually try and not just listen to the teacher and then do repetitive exercises, but actually, especially if they're given the opportunity to investigate and discover something, the maths becomes much more meaningful as well as more interesting.
Yeah, they get a lot more ideas of other things they can do with maths when they're doing an activity like this. Definitely engages them much more in the maths of the maths, in the subject itself.
Now we've got many. I mean, there are about with 371 proofs of Pythagoras' theorem, apparently subtly different from each other.
It's not infinity.
No, they were published in a book in 1927, and there are more different proofs as well. So, but we're going to concentrate in the next few weeks on the jigsaws and the way some proofs that are what I referred to as proofs without words. And next week, Caroline will have a visualizer and she'll show you how the pieces of the jigsaw are put together. And we'll be doing something similar to today, but with different stories to tell about it, and definitely a different puzzle. And I do think that they make a really good way for children to young people to explore mathematics, think about how to prove ideas, and to revise things like Pythagoras' theorem by looking at them in a completely different way.
And it makes it a lot easier to visualize it as well, because you can then picture these pictures and the two little ones, smaller ones, their squares added, it's the same as the square of the big ones. It really helps to have that, for me anyway, to have the visual image.
As you see here on our last slide, so it's almost time to say goodbye.
And it is time, so we've just got enough time to say goodbye. So next week, more Pythagoras, more puzzles, and are we doing more history next week, or are we done?
Oh yes, I mean there's more stories to tell and more ideas, because these puzzles that we're going to one of them's by Leonardo da Vinci, by the way.
Oh wow, okay, cool.
So we'll talk about, and I mean, that wasn't proved yesterday.
No, exactly.
And we're going to tell a little bit of a story about each one, and in its time. When there's one that was proved by Einstein when he was 12, apparently. Now, actually, he didn't do very well at school at all, but he was obviously very bright.
Yeah, no, that's surprising because the story is he didn't do well. He wasn't. Well, I don't know if he wasn't academic, but he didn't do well, and yet he proved Pythagoras'
I think
theorem.
I think he probably was academic. He just didn't cooperate very well.
Yeah, he just probably thought they were all idiots.
He's a bit like.
Leave me alone and let me do my mathematics.
Well, I don't know that was even the case. He was probably a bit like Winston Churchill, who did very badly at school, but was really quite a cultured and an intellectual. And wrote lots of books about history as well as being a politician. But he didn't do well at school either.
Yeah, no, maybe there was just there's a lot of memorization back then, wasn't it? It's pretty much purely memorization and repetition. So probably just was bored, most likely.
Maybe. Anyway, I think it's 6 o'clock here and time to say goodbye.
I think it's 6 o'clock here too. Thank you very much, and we'll see you next week, same time, same place.